it's a little strange to open this new section with a problem that we're so familiar with, the tangent line. But I wanted to do this because linearization and the differential is exactly the same problem as finding the tangent line. To see what I'm talking about, let's start with this example. I've got the square root of x, and ignoring some scaling issues, that's what the function looks like. That's the square root of x. So the tangent line, so let's say that we look at the point 2, and we want to establish the tangent line there. We can use our tangent line to make approximations to our function as long as we don't travel too far away from our initial point. Right? If you try to make an approximation for this y value on your function, that's a little bit too far away, right? This is quite the large error. But if you only travel a small distance away, then your tangent line approximate your function pretty well. And this all comes from using Leibniz notation. If dy dx is equal to the value of your derivative, you can kind of think of it as throwing the dx onto the other side. So you find that dy is equal to f prime of x times dx, or the change in the y value is your derivative value times the change in the x value, right? The bigger you travel in your x direction, the bigger your y gap becomes, the change in the y's. So the main idea here is the actual change in the y values can be approximated with the dy part of the derivative, which is your derivative value times the dx, or the change in the x. All right, but let's just go back to this problem. This problem just wants us to warm up by finding the tangent line to a point. So here's our square root of x function, and we are interested in point x is equal to 4. So over here at 4. So in fact, let's try to scale that properly. I should only get a 2 when I'm there. There we go. So the tangent line is going to be y minus y naught is equal to m times x minus x naught. So I'm using point slope form. And notice how that same pattern pops up. The change in the y's is given to us by the slope, or the derivative, times the change in the x's. All right. First, let's give ourselves the y naught and the x naught. So a point that we're interested in. So when x is equal to 4, the y value is a 2. And the slopes of our tangent lines are given to us by the value of the derivative. So the derivative is, oops, I don't think I'm ready to differentiate first. I first have to rewrite it. The original function is the square root of x. The derivative is then 1 over 2 root x. All right, if I plug in a 4 here, I get square root 4 is a 2, 2 times 2 is 4, 1 over 4. All right, so you can put that into mx plus b form, but that right there is a valid equation for the tangent line at the point of interest. And this section is all about traveling along that tangent line, using it as an approximation to the original function.